So in 1819, at room temperature, by using the data for the experiment which was performed at the room temperature. So in 1819, by using this room temperature data, Dulong and Petit, they empirically uh, found that the heat capacity at constant volume was somewhere around 3 into R, where R is the universal gas constant. Okay, so the heat capacity at constant volume was found to be 3R for most of the material. Okay, so uh, with whatever material they carried out the experiment was carried out, the data whatever was available. So few samples they had done, and there were lots of data available, somebody else's work. So they come out with the conclusion that CV comes out to be CV equals to 3 into R. That was their observation. Okay, where R is the gas constant. Now this formula is called as Dulong-Petit law. CV equals to 3 into R. This formula is called as Dulong-Petit law. Shall we proceed?
Yes, sir.
Okay. Now there is why there is a three term here, and why the formula comes out to be 3R only. So there is an explanation for that. This was the empirical formula based on the observations. So what could be the reason why the CV is 3R only? Why not any other number? Okay, why not 2R? Why not something else? Why 3R? So there is explanation for that. An explanation is as follow. So we all are aware of the fact that you take any material, any solid sample you take, it consists of a large number of atoms. Okay, and all these atoms uh, their arrangement is kind of periodic. Okay, are you getting my point? So a solid sample, if you take, it consists of large number of atoms. All the atoms, they are placed periodically. Their arrangement is not random. In case of solid, they are placed periodically. Am I right? Are you getting my point?
Yes, sir.
Okay. So if you take a solid sample, all the atoms, they are placed in their lattice point structure periodically. There is no randomness as far as the position of the atoms is concerned. So in a solid, each atom located at fixed lattice points, they are arranged in periodic order, but all the atoms, they are not at rest. They are not at rest. Okay, they they oscillate. Although the amount of oscillation is very small, their displacement, their amplitude is very small, but still they are oscillating. They are not at rest, even at room temperature. Even at room temperature. So in a solid, each atom moves by a small amount about their equilibrium position, about the position where they are residing, their actual position. Okay, so they moves left, right, they moves up, down. So there is a moment, a three-dimensional moment of every atom inside the solid. So even at room temperature, and there is a quantum mechanical explanation further, uh, which you must have already learned, that the concept of the 0 point energy. So even at 0 Kelvin, if the sample really has zero energy, so that is a slightly different thing. I'm not discussing that thing here. My aim is here to find out the specific heat of solid. Okay, so every atom, even at room temperature, is not stationary. It moves by small amount about its equilibrium position. Is it clear to everyone? Yes.
Yes, sir.
Okay. Now, since as we have seen, since the movement of the atom around the equilibrium position is very small. Okay, the displacement of atoms from their equilibrium position is very small. So therefore, the restoring force the force which tries to bring the atom back to the equilibrium position. The restoring force is proportional to the displacement, like the spring. Okay, you stretch it, the restoring force will try to bring the spring back to its equilibrium position. So there is a restoring force acting onto the spring. Similar logic can be applied to this as well, because the atoms, even though it keeps oscillating, but eventually tries to go back to the equilibrium state. Okay, so the restoring force is proportional to the displacement, very much similar to your F equal to minus k into x. Okay, so this implies that each atom inside the solid, it performs a simple harmonic motion about its equilibrium position in three dimensions, in all three dimensions. Okay, plus x, plus 5 minus 5, plus z minus z. So there's a possibility. Okay, it will not happen that it is moving only along plus x and minus x. So if you take into the consideration, if you take this as a concept that every atom is oscillating around its equilibrium position, and every atom can now be treated as a simple harmonic oscillator moving, having degrees of freedom in three-dimensional case, then we will be in a position to find out the heat capacity at constant volume. Now, how we can find out the heat capacity at constant volume? So we will have to try to calculate the energy of the whole structure. Okay, energy of the whole structure, and we know that you can find out the energy of an oscillator very easily. See how the theory is moving, assumption or postulate towards finding the specific heat capacity at constant volume. Okay, so every atom is considered now here uh, as a uh, as an oscillator, simple harmonic oscillator. Now, if the vibrations of each atom in the solid is resolved into three components along x, y, z, then a three-dimensional oscillator can be represented by three one-dimensional oscillators. So instead of taking one three-dimensional oscillator, okay, if you can resolve its movement along x, so x along x only, you take only one oscillator along y, another oscillator along z, third oscillator. So maybe you can note down uh, uh, a three-dimensional oscillator can be considered as a three-dimensional oscillator one. Okay, only one three-dimensional oscillator can be considered as equivalent to can be considered as equivalent to equivalent to three three oscillators moving in one direction. Okay, so three individual one-dimensional oscillator. This is the approach, so that the calculation will become very easier for us. So a three-dimensional oscillator. So every atom is like a three-dimensional oscillator. Every atom is like a three-dimensional oscillator, and here we are assuming that a three-dimensional oscillator is equal to three one-dimensional oscillators. So every atom is like a three-dimensional oscillator. It can move left, right, up, down, left, here and there. Okay, plus x, plus y minus y, plus z minus z. Every atom can having that freedom to move along three-dimensional structure. Okay, but we are simplifying it further, and we are assuming that every atom is now equal to three one-dimensional oscillator. Every atom is now like three one-dimensional oscillator. Clear? Now, now the internal energy of the solid resides, it is there, resides in the vibration of its atom. So whatever energy of the solid is, it is because of the vibration, atomic vibrations of the structure. Okay, so the atoms which are vibrating, uh, that gives the energy to the solid. Okay, so internal energy of the solid resides in the vibration of its atoms. Clear?
Yes, sir.
Okay. Now, now we are coming to the our aim. Aim was to find out the heat capacity at constant volume. Now, what happens actually? So when the solid sample is heated, again and again we are using this term solid. So right now we don't know whether this solid is aluminum, whether this solid is a silicon, semiconductor, conductor, bad conductor. We don't know anything. But the whole theory is developed for the solid. Okay. So when the solid is heated, when you heat it, what happens to the internal energy when you heat the solid? What your observation? Or theoretically, what should happen? You know that solid consists of large number of oscillators, large number of atoms. Every atom is a kind of oscillator. When you heat the solid sample, okay, so when the solid sample is heated, the internal energy of the solid increases. Why increases? Because the vibrations of atoms becomes more rigorous. Okay? So when you start heating the sample more and more, the atoms, the oscillators, it gains energy, and because of that energy, the amplitude of oscillation also increases, and therefore the internal energy of the solid increases. Clear this slide?
Yes, sir.
Okay, good. Now, then how the heat capacity is defined? So the molar specific heat is defined as the rate of change of vibrational energy, that is the internal energy, of 1 mole of a solid with respect to the temperature. Okay. In lower classes you have learned the definition in this wording: the amount of heat required to raise the temperature of 1 mole of a substance by 1 degree. Same statement I am rewording here in the upper three lines. So the molar heat capacity, which is the amount of heat required to raise the temperature by 1 degree, is nothing but the rate of change of vibrational energy, that is the internal energy of 1 mole of a solid with respect to the temperature. So see here, the heat capacity at constant volume is nothing but the rate of change of vibrational energy, that is the internal energy of 1 mole of a solid with respect to the temperature. Now, uh, uh, given the definition, you know, there are so many atoms in a given solid sample, and there will be so many oscillators. So is it not simple for us to find out the heat capacity theoretically, because it is simply the derivative, no, du by dt, where u is the internal energy. Am I right? Do you all agree
Yes,
with
sir.
me?
Yeah, yeah.
Okay, if u is the internal energy, so as the definition says cv, the heat capacity at constant volume, will nothing be is nothing but equal to uh, cv equals to du, where u is the internal energy, du by dt. Okay, so rate of change of the vibrational energy with respect to the temperature. So therefore, Cv is what? Dabba U by dabba T at constant volume. So U is the internal energy. So the rate of change of vibrational energy with respect to the temperature for 1 mole of a substance. So this is what Cv is. And in lower classes, the same definition you have learned: the amount of energy required to increase the temperature by 1 degree Celsius. Am I right?
Yes, sir.
Okay. But how to find out theoretically what is the internal energy of a solid sample? So let's consider 1 kilomole of a solid sample. 1 kilomole of a solid sample. Let n zero be the total number of atoms in the solid, where n0 is the Avogadro's number. Okay, let a solid comprised of n0 number of atoms. N0 is the Avogadro's number. Now here, if you have n0 number of atoms, so you will have n0 three-dimensional oscillator,
Yes.
or 3n0 one-dimensional oscillator. We assume that a solid comprised of n0 number of atoms, n0 is the Avogadro's number. So the solid sample will contain, n0 number of three-dimensional oscillators, which is which is equivalent to uh, 3 into n0, which is equivalent to 3 into n0 number of one dimensional oscillator. I suppose this you have understood. Now, therefore, uh, now, uh, total number of oscillators are known to you. So if you can find out, if you can find out energy of every oscillator when it is oscillating, if you can find out energy of every oscillator, so don't you think that you can find out the total energy? You know the total number of oscillators. If you can find out the energy of every oscillator, don't you think that you will be able to find out the total internal energy?
Yes, sir.
Okay, so we can use the equipartition. So the Dulong and Petit, they have used the law of the equipartition of energy theorem, and the according to which the average energy of every one dimensional oscillator, average energy of every one dimensional oscillator is kT. Okay, half kT for potential, half kT is for the kinetic. So total average kinetic energy of one dimensional oscillator, average energy of one dimensional oscillator is 1 kT for every one dimensional oscillator. So Dulong and Petit, they assume that the law of equipartition of energy can be applied to the oscillators atomic structure which are there inside the solid, and they assume the formula which comes out to be kT. So average energy of each oscillator, one dimensional oscillator, is kT inside the solid. The energy of average energy of one oscillator. Now you have 3 n0 number of oscillators. So what will be the total energy? So if you have 10 oscillators and average energy of each oscillator is kT, then for 10 you will get 10 kT. Internal energy will be 3 n0 into kT. Now n0 into k is the R, n0 is your Avogadro's number, k Boltzmann constant. So that product is R, a gas constant. So the total, so therefore the total internal energy of the solid having 3 n0 number of oscillators is U equal to 3RT. Now you know the formula. Heat capacity at constant volume is dA by U by dA by T. So if you take the derivative of this with respect to the temperature, you have U equal to 3RT. So it comes out to be 3R. And this is what was the observation, the observation by Dulong and Petit, that most of the solid, they have the heat capacity at constant volume, that number equal to 3R. Okay, that was the observation, and they derived the formula which is the same 3 into R. So which means that whatever assumptions they have made, that a solid consists of n0 number of atoms, every atom is like a three-dimensional oscillator. A three-dimensional oscillator can be assumed to be a one-dimensional, three times one-dimensional oscillator. Internal energy of the solid resides in the atomic vibrations of these oscillators. So whatever assumptions they made, it is more or less, because the formula comes out to be similar. It is in good agreement with the experimental observations. So more or less, uh, people thought that yes. So this is what the process must be happening inside the solid. So is that clear to everyone?
Yes, sir.
But but there is a problem. So the formula which we are observing here, Cv equal to 3R, it is not valid for whole range of temperature, right from 0 Kelvin up to say 500 Kelvin. It is not valid. Although the formula Cv equal to 3R is valid, most of the solid, they have the heat capacity at constant volume, that number, that value equal to 3R, but it is not the for the entire spectrum of the temperature from 0 Kelvin to the 500 or 600 Kelvin. It is the formula. The formula is uh, here. So y-axis here is the heat capacity at constant volume. X-axis is the temperature, and this is what the Dulong and Petit theoretical formula is. Cv equals to 3R. Can you see this horizontal line which I am drawing
Yes,
here?
sir. Yes,
Okay.
yes.
Okay. But The experimental observation is slightly different. It is like this. So if you can see the mouse pointer which I am moving around here, so the diamond structure is here, stone here, silicon is here, aluminum and lead. So if you see the nature of the curve for all these samples above 300 Kelvin. So for the higher temperature above 300 Kelvin, 300 Kelvin means to room temperature. So above room temperature up to 1000 Kelvin. So all the samples, their CV values, their CV value 10, their CV value 10 towards 3R. All the samples, all the solid samples, their CV values at higher temperature, more than 300 Kelvin. Here, if you see, okay, so their CV value approaches 3R. Are you getting my point?
Yes, sir.
But so for higher temperature, it approaches 3R. But at lower temperature, the value is not 3R. It is different. Lower temperature, it is not 3R. It is not constant. It is varying with respect to the temperature. And if you notice, uh, all of them, all of them here at zero temperature, they are having CV equal to 0. If you notice here from this graph, yes, experimental values of CV, if you can see the mouse pointer which I am moving around here, the experimental values of CV, the heat capacity at constant volume for lead, aluminum, silicon, and diamond, although at high temperature, each of them are approaching towards 3R, which is very much in good agreement with the Dulong-Petit theoretical formula. But at low temperature, CV is not 3R, it is much less, and at 0 Kelvin, the CV approaches to the value of 0. So this is what the problem was. So although at high temperature, the Dulong-Petit law was matching very well with the experimental observation for many solids, for most of the solid, almost all the solids, the value is 3R, but for lower temperature the value is not 3R. So there was something wrong with the Dulong-Petit law. Many textbooks they write Dulong-Petit law as the law of CV at higher temperature. At higher temperature means at higher temperature the Dulong-Petit law is very much valid. Dulong-Petit law is has the acceptance because the value matches with the experimental observation. But at lower temperature, the formula is not very well appreciated. There is something which needs to be look into it, which needs to be incorporated. Something else, something was wrong with some assumption or one of the assumptions. Something went wrong.